So the main use that we will do of generating functions is to describe, to use them for a sequence of probabilities, okay? So if you take an integer random variable, so a random variable that takes values on the integers, then the probability that x is equal to n, it's a sequence. It's a sequence of positive numbers. So we can associate to this sequence a generating function, which is just defined as usual. Okay. Okay. So notice that you can also define. So this definition tells you that the generating function is the expected value of s raised to the power x. Okay, because if you compute the expected value of s to the x, you exactly get this expression here. Okay, and so this is will be very useful to remember. Okay, so there is another. We can also consider the cumulative generating function. So we can also define the probability that our integer random variable is larger than n, and we can call this Qn. Okay, and then we can define the associate generating function in the usual way. Okay. Now, of course, Pn is Qn minus 1 minus Qn. So the probability that x is equal to n is the probability that it is larger than n minus 1, but that it is not larger than n, strictly larger than n. So there is a relation between this generating function and this generating function, and this relation is easily obtained from this expression here. So if you, so of course this expression holds for n positive, but for n equal to 0, you have that P0 must be equal to 1 minus Q0, so the probability that x is equal to 0 is 1 minus the probability that x is larger than 0, okay, if you read this. And so if you use these two equations, you multiply this by s to the n, and then you sum over n from 1 to infinity. Well, what do you get? You get, on one side, you get P of s minus P of 0. And on the other side, you get, here you get s times Q of s. And then here, when you multiply by s to the n and sum over n from 1 to infinity, you get Q of s, apart from the term n equal to 0. So plus Q of 0. Okay. Now you see that then because this is equal to so you can rewrite this by saying that Q of s is equal to 1 over s minus 1 times P of s minus P0 minus Q0. but P0 plus Q0 is equal to 1. Okay, so the relation that you find is that this is equal to 1 minus P of S divided by 1 minus S. Okay? Okay. So, of course, P is a probability distribution, so it is normalized. So one property of the generating function is that when you compute it in S equal to 1, then you should get 1. Okay, because when S is equal to 1, this disappears, and you just get the normalization of the probability. Okay. Okay, so but there are a lot of other interesting property that you can extract from the behavior of this function close to S equal to 1 by taking derivatives. So if you take the first derivative and you compute it in 1, so what happens? If you take the derivative of this, here you get n times s to the n minus 1. When you compute it in s equal to 1, s to the n minus 1 is just 1. So you just get sum over n, Pn times n. Okay? So this is just the expected value of x. Okay? So this also, you get it from this expression here, because you see that when you take the derivative with respect to s, x gets down, and then you get x times s to the x minus 1, expected value over x. When you take s equal to 1, then s to the x minus 1 is equal to 1, and you get just the expected value of x. Likewise, if you take the second derivative and compute it in 1, you get the expected value of x times x minus 1. Okay? And so if you take n k derivatives of in S, then this will be the expected value of x times x minus 1 times x to the etc. times x minus k plus 1 times s to the x minus k plus s to the x minus k. And when you compute it in s equal to 1, then this is just 1, s to the x minus k is just 1, and what you get is just the expected value of x of this product here, which we call it xk. Okay, so you in principle you can get all the moments from the derivative of the generating function in 1. And also another interesting property is that if you take the limit as s goes to 1 of q, then you see that p of s goes to 1, but also s goes to 1. So so this limit, you have to perform the limit with the L'Hopital rule. So you have to take the derivative up here is minus p prime, the derivative down here is minus p. So the limit when q goes to 1 is just the derivative of p in 1. So the expected value of x is also given by q computed in 1. Okay? And okay, so how do you use these relations? Say, for example, you can see that the variance of a random variable x is the expected value of x squared minus the expected value of x squared. So this essentially you can compute it from the second derivative and the first derivative of the generating function. And if you do a little bit of algebra, this is the second derivative plus the first derivative in 1 times 1 minus the first derivative in 1. Okay, so by taking more and more derivatives and computing them in 1, then you can compute all the moments of the random variable. Okay, so another very interesting property of generating functions is that for integer random variables is what happens when you have sums of independent random variables. Okay, so imagine that you have two random variables x and y that are independent, and then you want to compute the generating function of the sum of these two random variables. Okay, so the definition of this is that this is the expected value of s to the x plus y. Okay? But now s to the x plus y is s to the x times s to the y. And the two random variables are independent, so this sum here is really a sum of x over p of x times the sum of y of p of y. So essentially you can factor this object into the expected value of x, of s to the x, times the expected value of s to the y. And what is this? Well, this is the generating function of x, and this is the generating function of y. Okay, so what we find out is that the generating function of the sum of independent random variables is just the product of the two generating functions. And so this is very useful because it allows you to do a lot of calculation. In particular, you see that if you compute the analogous, if you compute the probabilities, so the probability that x plus y is equal to n, this is given by a very complicated object which is called a convolution. Plus the probability that x is equal to 1 times the probability that y is equal to n minus 1 plus etc. plus the probability that x is equal to n times probability that y is equal to 0. Okay, so So if you want to compute directly the probability that x plus 1 is equal to n, then you see that you have to do this complex operation, which is called a convolution. And this involves essentially n plus 1 multiplication and n additions. Okay? Whereas what you can do is, if you have the generating function of the random variable x and y, you can compute the generating function of x plus y by just one multiplication. Okay? Okay, so now this, of course, generalizes to the case where you have many random variables. Okay, so if you have a random variable which is the sum of n independent random variables, then the generating function of the sum is the product of the generating functions. And if you have a particular case where you have a sequence of random variables that are independent and identically distributed, this means that these variables, this term IID, means that these variables are independent, mutually independent, and that their distribution is the same, is identical. Okay? So then if you have this sequence of random variable, you can compute the sum of these random variables, and you can ask what is the probability distribution of this of the sum. Okay, working with generating function is much simpler because it tells you by exactly what I told you before. It tells you that the generating function of the sum is equal to the generating function of is equal to the expected value of s to the x1 plus x2 plus xn. And as before, you can factorize this n times. So, but each of these factors will be equal to the generating function of x, computed in s, and you will have n of these factors. So the generating function of n of the sum of n IID random variables is equal to the generating function of these random variables raised to the power n. Okay, so for example, one simple application of this is now you can use this equation and compute what is the variance of Sn. And you can use the relation that I wrote before, and because essentially when you compute, say for example, the first derivative of the generating function of S of n will be given by n times the generating function of x to the n minus 1 times the first derivative of this generation, the generating function at n. So if you compute this in s equal to 1, this will tell you that the expected value of Sn, when you compute it in s equal to 1, this gives you the expected value of Sn is equal to n times, this is going to be 1, because when you put s equal to 1, p of x is 1, and this is the expected value of x. So this is equal to n times the expected value of x. Okay? So likewise, you can derive a similar equation for the variance. you have to work a little bit more. In particular, you have to use the fact that the second derivative of Sn, when you take two derivatives here, you have to take a derivative here, so you have two terms. So you will have n times n minus 1 times p of x to the n minus 2 in S p prime x of S squared, because you get, when you take twice the derivative here, you get two first derivatives. And then you have the derivative here, plus n times px n minus 1 of S times the second derivative of the generating function of x. Okay. Now, if you use the equation that relates the generating the variance to the generating function for the random variable Sn, which is, I remind you, is this one. And you use these two equations here. So what you find is that the variance of a random variable, of an integer random variable, is n times the variance of the random variable x. Okay, which is a very simple result. Okay, so let us make an example of this. And so let us start from the simplest random variable that we introduced, a binary random variable. So for a binary random variable, x can be either 1 with probability p or 0 with probability 1 minus p. Then the generating function is just, it is, you have the term s to the 0 with probability 1 minus p plus p times s to the power 1. Okay, so this is the simpler, the simplest random variable, the simplest generating function. Okay, so the expected value of p is equal to the expected value of x is equal to p, and you can use that equation and find that in the variance, the second derivative is equal to 0, so that the variance is just p times 1 minus p, if you use that equation. So, what about Bernoulli trials? So, Bernoulli trials is the problem where essentially you have a sequence of these random variables, n of these random variables. Each one can be either 0 or 1 with these probabilities, and you are interested in the sum. And these xi are all IID random variables with this distribution. Then we can use that result there and say that the generating function of the Bernoulli distribution, of the binomial distribution of Bernoulli trials is just 1 minus p plus p times s to the power n. Okay. Now, again, from this you can compute mean and variance. It's very easy. But another thing that you can consider is the limit when n goes to infinity and p is equal to lambda divided by n. that, as we said, in this limit, the binomial distribution should converge to the Poisson distribution. Okay, so indeed, if you do this limit, this is so you can write this expression in this form, and you see that immediately that this is just this limit just gives you the exponential. Okay, so the generating function of the Poisson distribution can be derived quite easily from the limit of the generating function of the binomial distribution. Okay, and indeed, if you work out the power expansion of this, what you have to do is this is e to the minus lambda plus times e to the s times lambda. So the power expansion of e to the s times lambda, we know it very well. So this is just the sum n from 0 to infinity of e to the minus lambda times lambda to the n divided by n factorial. And this is times s to the n. And this is this coefficient here is precisely the Poisson distribution. Okay, so there are many other examples that we could do, but I would like to instead discuss a different problem, which is also which will turn out to be very, very useful to solve complicated problems. So imagine that you have the following problem. So imagine that you have the problem of a person that check email with probability p every minute. With some probability p, this person will check his email. And the number of emails that he receives by minute is a random variable. And let's say that this is distributed according to a Poisson distribution with some parameter lambda. Okay? So the question that we want to ask is next time that he will check email, how many emails will he find? And what is the probability that he will find no email? Okay? So let us try to formalize this problem. So this is a problem where we are interested in the number of emails is a Poisson distribution, is a Poisson random variable that he receives in any minutes. Okay? And so in minute I, he will receive a number of email which is a random variable which is distributed according to Poisson distribution. But then, and what we are interested in is the total number of emails that he receives next time that he check the email. But now, this time when he checks the email can be the next minute, can be 2 minutes, can be 3 minutes. So the time, this time is itself a random variable. Okay, so the probability. So there is a time t. Emails is checked. This is also a random variable. And what is the probability that this time will be equal to n? Well, with probability p, this time is equal to, so if I check, if this guy checks his email at minute n, then it means that it has not checked his email in the previous n-1 minutes, and this of course with probability 1 minus p to the n-1, and then he checked the email at minute n. Okay, so this is another distribution which is called the geometric distribution. Okay, so the problem here is that essentially we have a sum of a random number of random variables. Okay, where this random variable x has a certain distribution, and the random variable t of the number of terms as another distribution. Okay, so how do we solve this problem? And then the question we want to ask is what is the probability that this random variable, this number of emails is equal to 0? Okay. Okay, so problems of this type can be addressed by generative functions. Using the following idea. So let's say that you are interested in this random variable, which is a sum of a random number of random variables, and that the probability that xi are equal to a certain value of n is equal to, let's call it fn, and the generating function, the corresponding generating function, we will call it f of s. This is just the expected value of s to the x. And the probability that the t, this number of terms that I'm summing is equal to t, we are going to call it g of t, and the corresponding generating function is g of s, okay, which is the expected value of s to the t. Okay, now what we are interested in is in the generating function of this random variable here. Okay, and so this is so I can write it as expand this. This is x1 plus x2 plus xt. And now you see that I can split this expected value in two parts. First, I can take the expected value over t, and then the expected value over this x1 plus xt. But now I can use the fact that these xi are all independent and identically distributed, and so that this object is just the expected value of s of x to the power t. Okay, so this is the expected value over t of the generating function of x, which is f of s, raised to the power t. And what is this? Well, this is nothing but the generating function of t computed in f of s. Okay, because of this relation. So this is just g computed in f of s. Okay. So this is a very interesting relation. Say, for example, it can allow us to straight away to this question. So because, well, we know that in this case, f of s is just a generating function of a Poisson distribution, so it's e to the minus lambda 1 minus s. And the generating function of this is easily computed, so it's g of s is just p divided by p times s yes, times 1 minus p 1 minus 1 minus p times s. Okay, it's just a geometric series. Okay, so then if you apply that to this, then you find that so the answer to this question is the generating function of the sum computed in s equal to 0. Why? Well, because when you compute a generating function in s equal to 0, only the term with n equal to 0 remains, which is just a probability that that the random variable is equal to 0. Okay, and so this is g of f0 by this relation here, which is f of 0 is just e to the minus lambda. So it's just p e to the minus lambda by the way 1 minus p e to the minus lambda. Okay, so so this is a very very useful way to solve a complicated problem of this type. And of course, from this relation, you can find a lot of relations. Say, for example, if you want to know what is the expected value of the sum of these random terms, then you have to take the first derivative of this. And you see that the first derivative will be the first derivative of g times the first derivative of f. So, and these are the expected value of t times the expected value of x, which makes a lot of sense, which is also what you would get if you take the expected value here. And but also now you can also compute the variance. And now you will get a different result because in the variance of s does not only gets contribution because of the variance of x, but also because of the variance of t. Okay? And so I invite you to do this calculation. So what you will get is that there is a term which is proportional to the variance of x times the expected value of t, and this is what you would get if t were not a random variable. But then you also get a term which is proportional to the variance of t times the expected value of t squared. Okay, and I invite you to do this this calculation to sorry, the expected value of x squared. Okay, to check this this relation. Sorry, so this is the variance of Sn. Okay, so the variance of Sn is given by this expression. Okay.